All right. So let's talk about functions. All right. So we're going to talk specifically about writing your own functions. So we've seen a ton of different functions throughout this class, things like the combine, class, filter, all of these. We talked about ggplot function. We talked about t.test yesterday. And so, a lot of these were created by developers and maybe people who are researchers or were once students like yourselves. And so, maybe we're interested in doing our own. And so why create our own functions? And so I think there's a couple reasons why we might want to do that. And I think one of the key ones is to cut down on repetitive code. If you're finding you're doing the same thing over and over again, function can help you do that more quickly and efficiently with fewer lines of code. So you're doing the same thing over and over. It can help you organize your code into manageable chunks. This is something that I do quite a bit. Like I'll organize a section of code in a function that does some plotting or something like that. You can also use it to help avoid running code unintentionally. And finally, some of the names of functions we've used in the class maybe, are not super intuitive. You can use names that make sense to you if you write your own functions. Okay. So the general syntax for writing a function in R is like this. So let's kind of break this down. You're going to assign some name of the function. This would be like, what we were seeing, t.test, class, like the name of the function that ends up with the parentheses later. So you give it a name and you use the function. That's a little bit redundant. You supply it some arguments, and then either curly braces or on the same line, you'll supply what you want that function to do. What are the actions that your function is going to take? Okay, so let's see some examples. So here we'll write a function that multiplies some number or divides some number. Got to update that. But here we're dividing a number by 100. So let's kind of see that in action. So I'm going to write a function called div100. And I would like to use the function, and it's going to divide some number x that I supply. It's going to take whatever I supply and divide it by 100. Okay, so take a look at my environment. If I run that code, I now have a function stored. I have a custom function. And so if I want to apply this, say I want to div 100 of x where it is 600, I should get 6, right? Because it's dividing that number by 100. I could also take that x out. It's pretty smart. It's guessing in the order that you supply those arguments, and I get 6. And so importantly, when we run this kind of line of code, it makes the function ready to use. But if we want to actually run something and get some values, we'll need to give it some values to get started, to get some output. All right. So we saw just a moment ago that you can sometimes have curly braces or curly brackets that allow you to use functions that span multiple lines. Like say you have multiple steps in a function, you can also put it on a new line. And so we'll have to use curly braces to do that. So something like that, I often will break a line there and then add curly braces down here. So let's try, we'll run that code again. It's still in my environment, and then same thing. And so if you have multiple steps, the curly braces can help you stay organized. And we could try with a different number. Let's try with 10 at 0.1. All right. So if we want to return or spit back out something specific in the output, by default, R will return kind of the last object that you print. So here we're printing x divided by 100, but let's say there were some steps up there. It's going to take the last one and spit it back out. But let's say I wanted to have intermediate object. So let's say have an output intermediate. So I'm creating that object. If I run this, store that function, and run that function, it's not going to give me any output because nothing is being printed inside here. It's just saving an object inside the function, which doesn't actually create it in my environment. So if I want to print that object, I would have to do return output int. So let's try that. Store that whole function and then try to run this. And now we get the print to the console. So this can be really handy if I have multiple steps, as I mentioned. So let's say we have like our final output is output int times 4. and we want to return our final object. There we go. So again, that return piece of code, so return object, is going to be helpful when we either are storing objects or we have a little bit more complicated code. All right. So functions can take multiple inputs. So for example, I have X here, but let's say I wanted to, provide more arguments to my function. So I could do something like X comma Y. And let's simplify this a bit. So our function is currently X divided by 100. It's not using any value Y yet, but maybe I want to add Y at the end. Okay, so run that function, store it in my environment, and I can actually look at it if I click on this here. Like, let's say I had it farther up in my code and I didn't remember what it did. You can inspect it from the environment if you want. And so let's take, we had 600, and then for Y, let's add 50. All right. So 600 divided by 100 is 6, plus 50 should be 56. And if I wanted to, again, to try to be diligent and declare my arguments, I could have something that looks like that. I think, again, that can be a little bit more readable if you're trying to be reproducible and help other scientists or other folks read your code. All right. So functions can return a vector or other object with multiple outputs. So let's say I had a number that was output 1 and I had a number that was output 2. I could use the combine function and combine these into a vector. And so this is X and Y plus 2 is the name of the function. So if I run down here, X and Y plus 2, the first output should be X plus 2. So it'll be 12. And then the second output will be 3 plus 2 or 5. And so that's what I get, that resulting vector. So yeah, return can be a single value, or it could be a vector, or it could even be something like a list. Functions can have default arguments. So let's say you're using a function that you wrote like a lot all the time, and you can declare what you want that default to be. And this lets us use a function without an argument later. And so let's say I have a function, we'll call it div 100 plus y. All right. Let me actually save this div 100 as the original here before I get too off track. Okay, so let's do div 100 plus y as our function name, and we'll use function. And so let's say we want the default value that's divided by 100 to be 600. That's the one we've been using a lot. And then maybe we want that default value for y to be 50. So x divided by 100, so same thing, plus y. I'll run that, store it in my environment. I now have another function. I can inspect it if I want to. All right, so let's test it out. So let's do div 100 plus y as my function. And, I could tell it that I want to use 650 as my values in the equation. But I could also just not supply them, right? So it knows and it understands what the default value should be if I don't provide them. If I provided other values, those will take precedent. All right, so let's write another function. We'll just get some practice here or see some more examples. We're going to write a function sqdiff or square diff that takes two numbers, x and y, with the default values of 2 and 3. So we already know enough to get started. So let's do that. We know the name of the function, and we'll need the function. It takes two numbers, x and y, with values of 2 and 3. All right. And so then what's the meat of the function? It's going to take the difference. Okay. It's going to square this difference and then return that final value. All right. So let's see if we can get this to work. All right. So 2 minus 3 is -1. Squared should be 1. If I supply it with different values, all right, difference is 3. It should be 9. All right. And so, of course, you don't need the x equal and y equal as long as the position is the same as what you provided up here. All right. Before we move on, remember, I can also break line here. So if I want curly braces to keep things organized, I can do that. And by default, R will give as output the last thing that is printed inside the function. But if we want to be just extra cautious and, doing best practices, we might have a return in there. We should get the same thing. So lots of options for how you structure your functions. All right. So functions can really have any kind of input. They can have words, for example, or text. So here's a function with character type data. So we're creating a function called loud, and it's taking an argument word, just something I supply called word. And so what do we want this function to do? So we might be first turning that word into uppercase using toUpper, and then repeating that word 5 times. So let's create an output that does that. Rep of toUpper word, and repeat that 5 times. Return output. We'll save that function, and then we'll do loud where word equals array. All right. And if I wanted to change that word, it would be pretty easy to do that. And so we could imagine a scenario where we need to do a bunch at once, and we could run all of them and produce that really quickly. All right. So these are some more simple examples with, numbers and words as inputs. We've been working with single values, single variables, and character variables and such, not any tibbles or data frames yet. So how would we do this when it comes to working with data frames or tibbles? So let's talk a little bit about what this function might be doing. It's going to get means and number of missing values for a specific column in the data set. And so this could be really useful if you're trying to just check out a couple columns of your data and you don't want to have to copy that code over and over. You could create a function called getSummary, and that's going to be a function that takes a look at a specific data set and it pulls out a column name to look at. But as we recall, when we're working with tidyverse tibbles, we supply the column names usually without quotes. And so we want to make sure that R understands that that's not an object like throughout, right? Tidyverse functions already know, but we want to make sure that R knows how to handle that even when there's no quotation marks. So it's going to take that data set and it's going to create a summarized table where we have a mean, that is the mean of the column name with values missing, removed, and how many missing values were in that column by doing a sum of is and a and that column name. So let's create this function and kind of see how it works. So the function name will be getSummary, and it's going to be a function that takes a data set. It also takes a column name. And so the meat of the function is going to be whatever data set we provide. This is a stand-in value. It's going to take that data set and pipe that into summarize. And you can spell it summarize with an S or a Z. Either way is fine. It's going to summarize by taking the mean of that column name, which we have to give curly braces. So column name. And let's make sure we remove any missing values and NA count. Let's call it that. We'll do the sum of is and A of the column name. All right. So we've stored that function. And so if we want to take a look again, we can check out what exactly that function's looks like. All right. So let's try this. Let's get a little bit of practice with some data sets we've seen before. So let's read in the ER data set and let's send that on over to the getSummary function that we created. Let's do the data set is ER, right? That first argument that I asked for, right? It's a stand-in for the data set. Now I'm actually supplying the data set. And then that call name is going to be, let's do visits. All right. So I can see pretty quickly that the mean of the visits column is 7.19 and it has 303 NAs. And so let me just double check this with the summary function. All right. So what did we say? The mean was 7.19. Missing is 303. What a relief. It worked correctly. Sometimes I get a little nervous that it might not be. All right. So that looks okay. And let's see. If we wanted to quickly change that, we only have to change it one place. We don't have to replace the column name multiple times. All right. So let's try with another data set. We don't actually have to change anything else other than those two arguments. So again, getSummary, it should work with multiple different data sets. We'll use yearly CO2 and whatever call name we're interested in. Let's do the year 2012. All right. So we got mean emissions and no missing data, which is pretty good. But again, we could quickly change the column that we're looking at. Okay. So in summary, simple functions are going to take the form of new function. This is whatever name you want to supply. You can call it my function, or you can call it, something describing what the action of the function is. You're going to use assignment and function, this written out. Inside regular parentheses, you're going to supply any arguments that you want to give the function. They can be whatever you want. You can supply a value, a variable, or a data set, whatever object you want the function to work on, or whatever kind of object. And then you supply the meat of the function, typically within these curly braces. So I've given it arguments X and Y. Inside is where I'm going to tell R what to do with them. If you want to supply default values, let's say typically your default value is 100, but occasionally it's like 95 or something, you could supply a default value of 100. In here, we're supplying a default value of 1. So X is equal to 1 unless you say otherwise, and Y is equal to 2 unless you say otherwise. So by default, the meat of this function, if you don't give it any values, is going to give you 1 plus 2. It's going to spit back out the number 3. And then finally, if you're working with lots of objects, especially if you've got a little bit more complicated function, you can use return to give you a value specifically for your output. And then very helpful tip, if you are creating functions that handle tibbles, especially, you're working in tidyverse flavor of R, like we've been doing this whole time, you can specify a column from a tibble using the double curly braces. Okay, so that gets around the confusion R might have about whether it treats it as an object or a column name. All right, I want to pause here to see if there's questions about any of the function-related stuff we just chatted about. Otherwise, we'll go into lab. I might have to see exactly what you're hoping to do, but I think that maybe a case when would be appropriate. Not sure you would need to use a function here, but depends on so if you wanted to do that to multiple comment columns, we'll talk about that actually in the next part of this module. A quick question about the function working for you. So let's make sure we set it up the same way. And so, because if you wrote something, get summary, and it's slightly different, let's make sure that the function itself is the same. And definitely want to make sure you have the ER data set as well. So really briefly, I'll copy this into the chat in case that's helpful. Yeah, so definitely want to make sure that you actually run the line of code. I know that's maybe seems silly or something, but because it's right there, right? But we do have to run it to store it in the environment. So you definitely should see it over here. Yay! All right. And yeah, anyone who maybe was just watching and not actually plugging in the code here, definitely encourage you to check out the slides and run it, on your own time too, if you want to revisit this. Other questions? All right. Well, I think maybe the best way to get comfortable with this is to practice in the lab. So let's go ahead and do that. We'll see you all in there. Our first mission here, and so functions are a little bit about problem solving. So we're going to have to put on some thinking caps here. So our function is going to take one argument. It's going to take a vector. It's going to return the sum of that vector and square the result. We'll call it sum squared, and then we'll test it. The format should look a little something like this. So let's take a moment to figure out, what's the name of the function, what's going to go in here for X and Y, and what's the meat of the function going to look like. So let's try that for a moment. All right. Well, let's try to put this one together. So the name of the function is going to be that first thing we want. We want to call it sum squared. So let's put that first. We're going to want assignment and function. You'll notice it kind of glows in a different color. It's a little blue or something. All right. We also want to tell it, okay, what are the arguments? It's going to take one argument, a vector. And so I can call this whatever I want. I am deciding what the name of the argument is. So I could call it vect. Probably not vector because that's actually a function. So important. We haven't really talked about this too much, but you probably don't want to name an object the same thing as a function. It could make R be a little confused. So could call this vect, or maybe even my vect. or even x. X is fine too. All right, so it's going to do the sum of the vector and then square the result. So let's take the sum of all the values in x and then raise that to the power of 2. All right, so notice I now have the sum squared in the environment. And let's test it on this vector. All right, looks good. Anyone getting anything very different or has done something different with their code? All right, well, let's try another one. I can leave this here for now. Yeah, that's fantastic. Yeah, so you could save this as an object first and then plug it into sum squared. That's perfect. Lots of ways to do this, right? It's problem solving and there's multiple ways. It's funny. It's kind of like the opposite of math class where it's like, you know, the important thing is we get the same answer, but we might take different avenues to get there, right? So there's whole new meaning to showing your work. All right. So for this next one, let's create a function that's going to take 2 arguments this time. It's going to test whether the number 2, the second number, is contained within the vector. So we're just testing whether it's in there or not. We'll call it has n, and we'll test the function on the vector, on the same vector as up above, and the number 21. You should get the answer true because 21 is indeed inside that vector. So let's maybe do a little bit of setup and then we'll talk about it. All right, let's get into it. So we know what the name of our function should be. It should be has n, and we'll want to use the assignment and the function. And it's going to take 2 arguments. It's going to take a vector and a numeric value. So we could call this vect and n. So our arguments are separated by commas, and the meat of our function. It's going to test whether the number n here is contained within the vector 1. So we could just, doesn't have to be overly complicated. We could just say n in vect, and that should give us a true if it is and a false if it isn't vect. All right. Okay, so that's now in my environment. Just make sure we run that line of code. Okay, so has n, where the vect is this one, and n was 21, right? All right, so that's true. If I do the same thing and give it a number that's definitely not in there, it should give me false. And so we could imagine this might be really helpful. Like, let's say we're looking through a column and we're trying to see if there's a specific value. We're trying to look through a column for a specific value. We could do something like this. Okay. Again, anyone try anything different? There's lots of ways to do this. All right. So let's amend this function so that it takes a default value of 21 for the numeric argument. So let's just copy this. And the way we would specify the default value is by amending what's inside these parentheses here. So we could say n is 21 is the default value. So currently, if I look at has n, I don't see the default. So I have to make sure I run this code again. If I look at it now, I have to refresh it probably. There we go. So now I can see that default value. All right. So if I do has n of this vector here, and I don't even need to say vect, it's going to guess it's the first argument. The default output is true because 21 is inside there. But if I changed this to 25, it should get false. And I could still declare what that n is, but if I don't declare it, then it will take the default value. All right, so let's talk a little bit about how we could, do something with a data set where we want to do something to multiple columns. So we talked about kind of functions that we could write ourselves, but let's talk a little bit more about functions as a way to iterate or do something multiple times. All right. So, we just made a lot of custom functions that do something pretty cool, but there's also a base R function called sapply that can be really powerful for us to apply, hence the name, R functions to other things. So we've made functions, we can apply that function easily. And so sapply is going to take the form of sapply, this function, and you give it some kind of data frame or list or vector and some function that you want to apply to every item. So let's say we have a vector, with 5 numbers, and we want to apply the same function to all of them. All right. So for example, let's look at the ER data set. Remember that we have a bunch of different columns. So the different counties and all of that. We could take a look at it over here. got number of visits, year, and then the rate of visitation. If we wanted to maybe get the class of every column in the data set, we could do sapply on the ER data set. What do we want to apply to the ER data set? We want to apply class. And so this is a little different. It doesn't have parentheses this time, but it knows we're doing the class function. So let's see what that looks like. All right. So it's giving me each column name and then the class below. So it says character, numeric for all of those. All right. So you could also pipe it in if you wanted to. So just a slightly different grammar. All right. So we made that div 100 function earlier that we, let's say we wanted to use that to convert these 0 to 100 percentiles to proportions. We've got a bunch of numbers in the data set that are out of 100. So these confidence interval values. So maybe we want to convert them to percentiles. What we could do is say, hey, I'm going to select all of the columns that end with CL for confidence level and apply the div 100 function to them and then kind of spit them back out. So let's give that a try. Let's take ER and we'll select the columns that end with CL. So that would be those two columns, right? And we want to apply to both div 100 and just double check that I've got that in my environment here. All right. So some of them are going to be NAs if there was a missing value there to begin with, but any values that were not missing should look okay. Gives me a very long list of them. All right, there's the top. All right, we can also use a custom function on the fly. I like to call it to iterate. We also call this an anonymous function because we actually never give it a name. It's basically a function that exists once and happily disappears, right? It doesn't have a name saved in our environment. So how we would do that is instead of supplying div 100, what we could do is just explicitly put it in here where x is divided by 100. And we can just print out the head of what it gives us, and it gives us the same thing. So we could easily change this if we wanted to, maybe just divide by 10 or something, we could do that. So again, we're taking these columns and to them, we're applying the function that we provide here. And again, this is anonymous because it has no name. All right. And for those of you who may be a little bit more advanced or just curious, there is an alternative syntax you can use. You can use a backslash instead of the word function. R understands that to mean the same thing. All right. So let's talk a little bit about a function called across, which is actually, again, part of the tidyverse. So intended to work well with tidyverse functions, especially we'll see summarize and mutate. Okay. So we already know about how to use mutate and to calculate summary statistics using summarize. So for example, we might take the ER data set, we might summarize to get the max number of visits by taking the max of that column, and then the max rate by taking the max of the rate column. So we know how to do that already. All right. So let's talk a little bit about how we would apply functions with across instead of that sapply we were just talking about. Comes from the dplyr package. And so across is going to make it easy to apply the same transformation to multiple columns. So typically we're going to use that with summarize and mutate. So typically how this would look is we would summarize and then specify which columns to go across and then what function to do across those columns. So we're saying summarize across what and how. For mutate, we would say, okay, well, I want to change or alter my columns. So I want to go across what columns and what I want to do to those columns. So you're going to list columns first. You're going to list the function next. And if there are any arguments, you'll want to use an anonymous function. And so let's see some examples of this. Okay, so if we were to combine this with summarize, what we might do is say, all right, well, I want to summarize across columns visits and column rate. And I want to take the mean of both of these. So let's take R. We will summarize across multiple columns. Which columns do I want to summarize across? I want to do visits and I want to do rate. And then I want to take the mean of each of these. All right, so there's missing values, right? There were some NAs in the data set. So let's change this just a little bit to be a function on the fly or that anonymous function. just so that I can supply the argument. So let's do function x is the mean of x with na.rm equals true to remove any missing values. All right, great. So I have a mean number of visits and also the rate adjusted for the number of folks. All right, we just saw that. All right, and also it's going to acknowledge other tidyverse functions like group by. Let's say we wanted to do the mean for visits and rate, but also wanted it grouped by year. Don't forget our pipe. We could get that as well. And so each year has an average visitation and rate of visitation. All right, so we can apply functions with across. So we can use tidy select options to choose which columns. So remember, starts with, ends with, contains are all going to be very, very helpful when we're using them with across. And so maybe we wanted to just select those columns that contain CL or ends with CL. So we can do that way. So instead of saying, all right, I'm going to do visits and rate, I could say ends with CL to get those confidence level values, or contains, just depending on what I want. But again, those are going to search for the column names in question. Right. So typically summarize is only going to work with one column per line. And so this allows us to work with multiple columns. Any other questions? So the difference between group by and select. So grouping just changes the way that future functions work. So changes the way summarize works, for example. So it's just going to break down that summary table a little bit more detail. And select chooses columns. So if you have a select step before something else, it's hypothetically dropping other columns that maybe you don't need. So you're saying, I only want to select these columns for future. All right. So let's see another example with across with mutate, actually. So remember, mutate is a super handy function for cleaning your columns, right? We saw that how we cleaned up the values last Friday by choosing a column and mutating it. And so oftentimes we may have multiple columns that have very similar data, and we want to do cleaning that is very similar on all the columns, all the similar columns. And so we could combine mutate with the replace NA function, but maybe to multiple columns. And so just as a reminder, replace NA takes a data set and the values that you might want to replace with a particular value. So we could do something like taking the data set and we could mutate across, let's say, a couple of years. And across all of those year columns, let's replace NA, replace it with 0. And so you can kind of see that effect already here, looking at 1943 through 45. Instead of these missing values, NA, I have zeros. And so let's try that. So we had yearly CO2, and let's mutate across. Let's just pick a couple years. So let's pick the same years. So 1943, 1944, and 1945. And what we want to do is that replace NA function. So we're going to replace NA of the column in question, and we're going to replace it with 0. And let's go ahead and call this something so we can explore it a little. So going all the way over, let's go back one. So if we're scrolling these columns and taking a look at, these were missing for many, many years, but for 1943 through 1945, I now have zeros in the missing column. And so let's say you wanted to do the opposite, replace something with NA, or, clean all of your columns in a similar way. This would be a really nice approach to use across. And so X is a stand-in for whatever that column is. Okay, so we got a gut check here. I know we've learned so much and our brains are saturated, but we're going to do our best. So why would we use across? A, for efficiency, it's faster and less repetitive. B, it can calculate the cross product across the data, or it connects across data sets. Yeah, exactly. I agree. So it's efficient, right? So we could do each of these columns manually one by one, but if we had to do 10 columns, that would be really repetitive and it would take a long time to code out. right? So across allows us to do things a little bit more compact with less code and less chance for mistakes. Okay, so if you're really curious about this and you are seeing this and thinking, wow, this is going to be so helpful for my work, you may want to check out the PER package. So it is very similar in that it allows you to apply functions to multiple columns in a data frame. It's specifically intended to work with the tidyverse. We won't get much into it, but it is very helpful when you have maybe some irregular types of objects, or you just want to be a little bit more advanced in your iteration. So definitely encourage you to check it out. All right. So dealing with multiple data frames. All right. So I talked really briefly in data classes about lists, and lists are a little funky, but may actually be helpful for us to work with multiple data sets at the same time. And so let's say we're working with a kind of collection of data sets, right? We're going to call it a DF list for data frame list. And it's going to be a list of AQ, which is air quality. It's this data set that lives inside R. It's the ER data set and the yearly CO2 data set. So I'll just bring that into R. So what does DF list look like? It's got AQ. It tells me kind of the columns it's got. ER. It's got columns here that have seen many times at this point. And then yearly CO2. So should all be very familiar. Don't worry too much about AQ, but just knowing that it has ozone and other attributes over time. All right. So one thing I could do is use sapply to do some function across each of these data sets. So maybe I would want to say select the numeric columns, so not any categorical columns, select the numeric columns from all of these data sets. And so what this would do is it would take that list of data sets, it would sapply the function that we're giving it. It's applying select from the data set where the column is numeric. So let's see that in action. We'll do sapply and we'll apply the function select from the data set and where the column is numeric. All right. So if we take a quick peek, it's going to print out a lot more than we maybe really want to see. But from the air quality, all of these columns are numeric, so it keeps all of them. From the ER data set, it does not keep the county, but it keeps everything else. And then from the CO2 data set, it has dropped the country column. So it's only keeping the columns that are numeric from all of these different data sets. I'm going to reassign it there. All right. And so I could continue to do different kinds of functions with sapply. So I could say df list. I'm going to sapply the class function. Should get data sets for all of them, right? This one's a less fancy data frame, but then the rest of them are tibbles. I could get the number of rows for all my data sets. I could get the call names for all the data sets, or I could get a little fancier. I could do this function call means, which is going to take the mean of every numeric column where we get rid of missing values. And very exciting, I get a lot of mean values. So again, having the stuff stored in a list and then using sapply can help us do multiple things to each item of the list or each data set. All right. So we can apply our functions with sapply given a vector or a list, and then providing some function, some action we want to happen. We can use across to apply functions across multiple columns of data. And we typically want to use across with summarize or mutate. So remember, summarize is going to give me summary statistics, and mutate is going to help us create or clean, in this case, cleaning columns. And then sapply or PER can help us work with multiple data frames or tibbles within lists simultaneously. So if you need to do the same thing to multiple data sets, then you can definitely use this approach. All right. I did link to Posit's PER cheat sheet. I think it's helpful if you end up going that route. But of course, there's the cheat sheet for today. Let's go back to the lab. All right. Let's read in the Cal Enviro Screen data set using read_CSV. We've done this a bunch of times now. You should be feeling a little bit familiar with this one. All right. So once we get the CES data in here, we'll want to do some summary statistics on water contamination. And so maybe we want to use across to do multiple columns, and we'll choose columns about water using one of our tidy select, contains water, and we'll do the mean function. All right. I will give us just a moment to get some code down, maybe get started a little bit, and then we'll chat about it. All right. So let's kind of follow this general format. So let's take the data and we're going to summarize, right? And then immediately after, we're going to summarize across a number of columns. I like to break line here. I think that looks nice. So I want to tell it to look at all the columns about water. So it contains water, and I want it to do the mean. All right, let's see what that gives us. All right, so I've got like 6 variables. Let's try again, see if they'll all fit on here. Yeah. All right, so a couple of these look great. They're not missing any data, but some of these are. So let's convert this over to an anonymous function or function on the fly. So we could do function of X, whatever column is in question, and we'll take the mean of that column with X as a stand-in and dropping any missing values. All right, great. So you'll notice the ones that weren't missing any data, they are the same. Okay, so questions about the way this one works. All right, looks like got 1 thumbs up. Everyone else feeling good? You need another couple of minutes. That's totally okay. All right. Glad it is making sense. Okay. So here we did some summarizing with across. And now let's convert all columns that are percentiles into proportions. So very similar approach, but this time we're using across and mutate. We're choosing columns that contain percentile. We'll use an anonymous function on the fly to divide by 100. If you were being really fancy, you could still use div underscore 100 and check your work. It'll be easier if you use something like this to just check those columns. All right, so I'll give us a moment to try that. All right, let's give it a try. So let's take the data again, and we'll mutate across. We're going to mutate across columns that are related to percentile. And so let's do actually contains ECTL. Can't really see that, sorry. And then we want to divide by 100. So we could do function of the column where we take that column and we divide every value by 100. And let's take a look at CES percentile before we do the change. So I'm selecting the columns that contain percentile just to take a look at them. So ozone, particulate matter, diesel, particulate matter, drinking water. It's all different percentiles here. And so if I do the same thing where I'm taking select and contains percentile at the end, I can also look at them there. So if I run this chunk of code here, it'll take the data, mutate it to divide by 100, only on the percentile columns, just those. And I select that. All right, so let's compare. So here we had like 3.12, 36.3, and now it looks like those values are divided by 100. So I could reassign or assign this to a data set, CES proportion. And we learned how to write stuff to your file yesterday, right? So what if I wanted to save that? I could say, well, I want to write to CSV, CES prop, and I'm going to call it Cal Enviro proportions. All right. Thoughts or questions about this one? Yeah, I agree. Doing this stuff in Excel is a struggle. All right. And any questions on any of the topics on functions or anything else? Yeah, sure. Okay. So let's convert all columns starting with the string PM into a binary variable, true if the value is greater than 100 and false if less than 10. So we're going to do the same approach as up here. So let's do CES and not hit enter, where we do mutate because we're cleaning some columns. We're doing some modifications. So mutate is what we want. And then we want columns that start with PM. And so just to give us an idea, what does that look like? Let's do select just to give us a little sneak peek. Okay, so it's only 2 columns, right? So maybe in reality, like I could just do this manually, but maybe I deal with multiple data sets and sometimes there's more than 2 columns. We never know. All right. And so each of these should be true if greater than 10, right? So we could do an anonymous function where anytime the column X is greater than 10, it will spit back out true. Otherwise, it will spit out false. So let's see what that looks like. Let's do select, or actually, let's pipe that into Glimpse just to get a quick look. All right. So if we scroll all the way up to PM, I now have a logical where if it was greater than 10, it would be true. So we're all less than 10. These are all greater than 10. If we take a look at what they were, yeah, that does make sense, right? These are all less than 10. These are all greater than 10. And yeah, don't underestimate the power of a logical test. It can get us a very clean and concise answer without having to use case when, for example. So I find them really helpful. All right. And we'll take the code from the previous question and assign it to the variable CES dat. So let's give it CES dat. Okay. Boom. I have a new data set and PM 2.5. I do have some trues in here, so it's not all false. It's a lot of falses. Okay. So take that code, create a ggplot where the x-axis is asthma and the y-axis is PM 2.5, that column that we just modified. And we want a box plot and we want to change the labels. So let's break this down. So typically we'll want to start with ggplot as our function and we want to declare the data. And then we want to talk about the aesthetics, right? So I got to tell it what the axes are going to be. So let's do X is, what did we say it was? Asthma. And Y is P 2.5. Okay. I want to add on the flavor, right? So the geoms. And let's just see what that looks like to see if we have any issues with the code so far. So that looks good. And let's do labs where X is ER visits for asthma, PM, particulate matter greater than 10. All right. Okay. So taking a look at this plot, that is kind of what I would hypothesize, right? That if particulate matter, the 2.5 microns, I believe, is the measurement. Sometimes that can cause like lung irritation. There's a lot of particulate matter, especially like tire dust and things like that, can irritate the lungs. And so if that's higher, that might cause more ER visits. But, there's a lot of points that are quite high. And so I might want to do like a statistical test instead. But this would be a nice way to just visualize it if I was curious about exploring it. If I wanted to get real fancy, could just give it some color. All right. So hopefully that's making a little bit of sense. Any questions about those? All right, great. And again, the RMD version of the answer key, I think, was not updated, unfortunately. The HTML should be okay. But if you want to maybe wait a few hours after class, we'll try to get that updated. If you want to check your answers to any of the questions here. I think we were curious too, maybe about this one, which is kind of fun. So we could create a function to make plots where we have a column name and we're just going to say, all right, well, I want to create a column name where data is the CES data set. And the aesthetics are going to be the x-axis is poverty poverty's on the y-axis. Whoops. And then the column of our choice is on the x-axis. Those double brackets because it's a tidyverse function and we want to make it clear that it's okay not to have quotation marks. And geom point. All right, let's actually do that. And CES plot with lead and CES plot with housing burden. And so the nice thing is you could make tons of exploratory plots here, right? So we have tons of variables in this data set, right? Pesticides and drinking water and all these other attributes, measurements of the environment. So we could try a bunch of them. Let's look at call names of CES. Let's try cardiovascular disease. If I wanted to, I could add that trend line